Hello, and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you for joining us today. Welcome to our viewers from around the world. Please let us know where you are watching from. Also, welcome to listeners on the podcast version of SETI Live, available on most podcast platforms. So a road trip to a gypsum quarry in Algeria led Youcef Sellam on a journey of scientific discovery. And now we get to talk to Youcef Sellam about that journey, one that has led to the discovery of microbial fossils in Algerian gypsum and could be used to help detect traces of past life on Mars. So today I am joined by Youcef Sellam. Welcome in, Yousef. Thank you for joining me.
Thank you very much for the invitation, and very happy to be here.
And amazingly, Yousef, you are a doctoral student, so you have not yet finished your Ph.D. So this is all pre-graduation work for you.
Yes, yes. The work started in one of my masters, and then I followed up the work in my PhD here at the University of Bern.
That is fantastic. So let's kick this off, everybody. So Yousef, first thing, so have you found life in crystals?
What? So what we have found in gypsum is that these are microfossils. So they are remains of life, and that was trapped in gypsum around 5 million to 5.5 million years ago. While the gypsum was forming, as it forms so fast, it traps all the microorganisms surrounding him, so surrounding the gypsum, and then with time, these microorganisms, they fossilize and they remain as either carbon or crystals or both.
Okay, well that's really interesting. I didn't know you could find things that were that tiny in like crystals. So I want to talk more about this, but the reason that you're here is because there was an NPR interview of an article about this research and your journey in science. So as much as the research is interesting, so is your journey here. So how did you get your start in science and in this research itself? You said it was in your master's. So tell us the
Yes.
story of Youcef Sellam.
uh, um, I remember I started to be more interested into science from high school or even earlier. When me and my father, we used to watch documentaries, and I used to ask him a lot of questions that he couldn't answer himself. So then I was like, start to be so curious. And then he was also encouraging me to do science and to read about everything. So he was bringing magazines and books about biology, about some weird questions that scientists cannot answer, and so on. And then by time so I graduated from high school. I chose microbiology at the University of Wargla in Algeria, and then because I wanted to work with these dangerous microorganisms, like especially pathogenic microorganisms, and then I moved to France. I did two other masters, second in microbiology and the third one in paleontology, um, where I discovered the field of microfossils, let's say. So I start to more study the ancient traces of life. And then I choose to come here in Bern to work on instruments that are detecting this kind of traces of life.
That's amazing. What a great journey. I love hearing about how curious kids become scientists.
Yeah.
I'm going to welcome in some people and then we're going to get to talking about these microfossils. So we have people joining us from Ireland, Algeria, India, South Carolina, Sweden, Georgia, and British Columbia. So very exciting. We've got a nice global audience.
Yeah.
So let's start kind of at the beginning. I know you sort of said this in your intro too, but what is a microfossil?
Well, a microfossil, as the name already says, say like these are microscopic remains of organisms. So it could be a prokaryotic cell, like for example, a bacteria or archaea, as it could be also unicellular eukaryotic cell, like protists, for example, as it could be also part of microscopic eukaryotic organisms, like that's a small portion of a macroscopic organism. And the microfossils have, depending on their chemicals, the original chemical structure or the form, and also the environment where they are preserved, they might have different composition at the end. So it could be only carbon, it could be some minerals, or as for example, some microorganisms, they have post-mortem transformation. So we have minerals that are replace the carbon and so on, and it makes different type of microfossils that we can find in the geological record.
Okay, so very, very, very tiny is what we're talking about here.
Yeah.
What can they tell us about past life? What does this tell us about where they came from, how they, how they lived, how they died? What can we learn from this?
Yes. So if we are studying microfossils from recent geological depositions, as other fossils, they can be used as a proxy to, for example, tell us about the paleo environment of the deposition, where how was the environment when these fossils they were forming, trapped, for example, or these organisms they were trapped. And for example, if we find some microfossils of bacteria and we have evidence that this bacteria is a cyanobacteria, for example, and we know that cyanobacteria requires light, for example. Now, these cyanobacteria are living in a column water environment, and so because we know that light has, at least photosynthetic light has a certain depth of penetration, then we can say, for example, these cyanobacteria, they were living in a shallow water instead of a deep water and so on. So it can tell us a lot of geological deposition context. And as we go back in time and if we find microfossils, then it tells more about how life emerged and what was the fate of life afterwards. This is what kind of microfossils tell us.
Okay. So, well, I'm kind of blown away. I am not a microbiologist. I am not even a biologist. I am a physicist and a planetary scientist. So like little tiny animal things. I did master's work in geology. I have like some basis in paleontology from that, but I'm kind of blown away by this concept even. I'm going to welcome in some more people, and then we're going to get right back to the science. So we now have people watching from Massachusetts, Michigan, Missouri, New Mexico, Alabama, and Illinois. So the United States are well represented. So that's really amazing. We do have an international audience as well, as we heard earlier. So continue to tell us where you're watching from, and we will continue to shout those out. Okay, so Yousef, this seems like a very difficult thing to do. Like finding fossils in sedimentary rock is not exactly easy to begin with. You have to know sort of where to look and what to look for. You're doing microfossils. How do your detection methods work? How do you find these?
Well, that's the main question in saying if this microfossil is biological or non-biological. That's the main question that we should, and we name it in science biogenicity of the fossil. So we need to know if it is biogenic or non-biogenic. Like to assess this biogenicity, we have certain criteria that we have established studying many microfossils that we have on Earth. For example, the microfossils should at least resemble some modern microorganisms. For example, we need, for example, to assess we need to know the context of the deposition, if it is a deposition environment where we know that microorganisms can exist. For example, gypsum. Yeah, we know in modern gypsum we have like some microorganisms living with gypsum, within gypsum or on the top of gypsum layers. And also we have, as we go deeper in and smaller scales, we need to assess, for example, the composition. For example, we have some elements that can tell us that this is life. For example, the Knobs elements, the carbon, the hydrogen, the oxygen, the phosphorus, and the sulfur. We have some molecules also that can, so like lipids, amino acids, nucleic acids, for example. These molecules can also assess more the biogenicity of a microfossil. Now, in our study, we did a measurement method called LIMS, laser ionization mass spectrometry. LIMS, LIMS, laser ionization mass spectrometry. And
Okay.
basically, yeah.
Not the worst acronym I've heard. Go on.
Yeah. I also have problems with these names. So we have a couple of methods here. So that's difficult to retain. So basically, it's a laser pulse that is focused just in a small area to hit the sample. And then because we have very high energy concentrated in a very tiny area, then a small part of the sample will be removed and evaporized, let's say. And this tiny, small part of the rock will be ionized, making positively charged atoms. And then right above the sample, we have the mass analyzer. It's a 160 millimeter per 60 millimeter. I think for the US, the inches, I think 6.3 par 2.3 inches, which is the size of the mass analyzer. And then the atoms, the positively charged atoms, they will fly through the mass analyzer. All right, they will be accelerated, and then the mass over charge ratio will be obtained, and then we have a spectra of the different elements we have in our analyzed area in the rock sample.
It's amazing how spectrometry can be applied on so many different sciences. A lot of things come down to chemistry, and chemists will tell you that a lot. So you're using this method to find microfossils here on Earth in crystals like gypsum, which still, again, I'm blown away by the fact that there's biology living on a scale that is this small. How can we translate this method to Mars? Is this something that we can put on a rover? Do we need to bring back samples? What's the you have a rover behind you. So answering my question before I've even asked it. So how does this work how would this work for Mars?
Yes. So the instrument we have here is automatically. So we have softwares that are also built here at the University of Bern. By the way, the instrument is the whole system. I forgot to mention that the whole system was built and designed here at the University of Bern. So it's a Bernese instrument, and also with that we have developed the University of Bern developed software that can actually make all the manipulation automatically controlled. So we have software that can, for example, move the sample inside, and we can choose where we want to analyze the sample. It's very specific to this kind of in situ planetary investigations. And then this is transferable to Mars. On Mars we cannot be there, so we need to send rovers. And the instrument, of course, it will be on a rover, and it will be remotely controlled, like from Earth. Of course, we would need instruments that can remotely detect gypsum if we want to investigate gypsum. Let's say, for example, we have orbiters that can detect large areas. And then, for example, let's say we have sulfates, hydrated sulfates in a location. The rover will go there and then help it with cameras. We can also know from the layers which one is the gypsum, and then we go with the analysis using our instrument.
So for those of you who watch us regularly, we did talk to Dr. Janice Bork last week, and Janice Bishop. I had a coworker with a similar name. Sorry. So we talked to Dr. Janice Bishop last week, and she talked about using CRISM, which is on one of the Mars orbiters, and that is one of the ways that we use spectrometry to find these minerals on the surface of Mars. So that it all ties together, everybody. If you watch our study lives, they all tie together. So you could put this on a rover. Now, and if you have questions for Yousef, please ask them in the comments. We are watching for those. And I do see some good ones coming in. We could use this on a rover, but I kind of want to ask you something sort of personal here. Do you think we'll find evidence of past life on Mars with this method or any other, but specifically with what you're looking at? Do you think it will happen?
Well, this is a big question, and honestly, honestly, this is one of the most exciting questions that scientists want to answer. But the thing is, like, we have certain parameters that tells that life could have existed on Mars. For example, Mars had water on its surface some a period in its existence. We had rivers, we had lakes, we had even large oceans, and then we know that on Earth, when the water is present, then life is present. So this is one parameter that can be considered. The second parameter is that we have detected so far on Mars elements that are related to life. For example, carbon, the sulfur, the nitrogen, and the phosphorus. And these are directly related to life. We also detected clay minerals. And clay minerals, they are known to retain water and to absorb a lot of molecules, organic molecules. So either they will retain the necessary molecules for life, for microorganisms, or they will preserve the molecules that are left by existing microorganisms, but they're not anymore existing on Mars. So they work in both directions. And also we know that on Earth, there are some microorganisms that can resist a lot of extreme conditions. We have one bacteria that I think everybody knows, Deinococcus radiodurans, that resists everything, almost everything. So high radiation, it was tested for cosmic radiation mimicking Mars surface, and then it resists these conditions. So if we take these parameters only, then we can expect something like this, at least in the early early formation of Mars. But then, in the other hand, as I said, Mars is very harsh. It's a dry, cold, with a tiny atmosphere. So we have a lot of cosmic rays hitting the Martian soil. We also have so far not detected any direct evidence of fossilized life. And then the issue is that also, if we had fossils, then these fossils also can be transformed or modified by the conditions of Mars. So
right. Okay.
Either life is difficult to have, or even if we had life, then what was kept after that, as for example molecules, then they will be damaged, existing for these billions of years or millions of years. I would say billions of years on Mars. Then this is a challenging problem. And we have also what we have mentioned earlier, the non-biological formations of microfossil-like forms. So it doesn't mean that you will see, like, you will observe like a filament inside the rock. It means that it's a bacteria. So there are many other non-biological pathways that can lead of making some fossils-like structures. So it's very difficult.
This seems so challenging. I love it. I'm gonna welcome in people one final time here. We have people watching from Texas, California, Latvia, United Arab Emirates, New Hampshire. Thank you for letting us know you enjoy these talks. And I saw one more from England. So thank you everybody for joining us. I'm gonna kind of go into some audience questions here. because one of them is sort of where I was going to kind of lead into this. John is asking if you've analyzed any meteorites, or do you expect to analyze asteroids, meteorites for evidence of any clues of life? Now, I know this kind of relates to, we talked about this a few weeks ago when we were talking about the Bennu sample return and how they have found 14 of 20 life-forming amino acids in that sample. But is this something that you can, is your method something you can use as well to sort of maybe study that sample or any other, meteorite sample?
Well, I haven't myself studied any meteorites, but the instrument itself is built for in situ investigation of planetary bodies. So meteorites and comets are included. So of course, and depending on how much energy you will use and what kind of power you use, you either go for the chemical elemental composition if you use higher power, so you have atomic signature, or use ablation. Now we are talking about molecules, and we have one PhD student with us. She's working on detection of amino acids, fatty lipids, and these kind of molecules that are related to life. And we have already a lot of papers published on this regard. Now, I'm not an expert in the life emerging in asteroids, but I would say a lot of chemistry happening there. It can form some molecules, as also it can damage a lot of molecules. So so it's very challenging, and yeah. But yeah, when it comes to our instrument, yeah, of course we can use it on planetary bodies.
Great. That actually kind of leads into another question. This is kind of rolling along nicely. Zapfan is asking if the mass spectrometer could measure atoms only or complete molecules. So if it's only atoms, how do you decide that they were part of life? So kind of speak to both questions there.
Yeah. So I mentioned in the first question, but I will say it again. So it depends on how much energy you use, and the laser mode we apply to our we used with coupled with our mass analyzer. We can go from elemental composition to molecular composition. In my study, we used I used the elemental composition, but with the same instrument, we can use different laser mode and we can detect molecules, right? But as I was working on very old microfossil, I was more towards the elemental than the molecular. But if we want to investigate life that are present, for example, in, let's say, icy moons, and which is, for example, today present life, then we go for the molecular only, also the atomic. But so if only atoms, how do you decide? Oh, not only the chemical composition is, so to assess the biogenicity, to say that this fossil is biogenic, we need to have a lot of criteria, not only one. We go from the macrostructure to macrostructure to elemental composition to isotopic fractionation to molecular presence to minerals. By the way, in my paper, I talked about the dolomite and the clays and how they are related to life, for example. Mm-hmm. The more you have criteria, the more you're solid when you're saying that this is biogenic instead of non biological. So you have it depends on how many methods you use and how powerful your instrument is to assess these kind of different criteria.
So it's definitely the extraordinary claims require extraordinary evidence. You have to have a lot of lines backing it up to say this is biology. So you're not just going to be like, oh look, I think it's biology. You're gonna have that like 5 sigma certainty.
Yes, exactly.
Okay, so Brian is asking a more technical question, and I think I get what he's asking, but I'm going to pass it on to you here. Can you talk a little bit about the electromagnetic shielding present in the spectrometer? Does it account for measuring gain? Is it shielded from the outside so that what you are working on is really just that internal sample and not getting anything from outside of the spectrometer interfering?
So we work in a vacuum chamber. So we basically isolate our sample and instrument from the outside environment, you know. So we expect that. So we work in a very low pressure environment. So to have the perfect, or not the close to perfect atom migration inside the mass analyzer, and this is a requirement. And we also work in an like the particle-free rooms where our environment is we have less and um, you know particles that can interfere with our measurements. But when it comes to the what he said, sorry, electromagnetic field is what he said.
Electromagnetic shielding. So
Shielding.
keeping outside electromagnetic influences from adding to what you're producing.
Oh, this is okay. I think this is prevented only by the chamber being in the vacuum. I'm not sure exactly how this will be removed, but yeah, this is what I know.
So that's kind of interesting. From what I can kind of understand between the question and the answer here is that where you're working on it, you have it in a vacuum chamber. That's going to be difficult to have on a rover, obviously. I mean, Mars' atmosphere is thin; it's not a vacuum. So that might be something that needs to be looked into before that gets added to a rover to make sure that we do account for anything outside influencing it. Okay.
Yes. Yes.
Okay. I can understand this. Again, I am a physicist. All right. I'm going to have one last question for you, but I have one last audience question for you that I think is kind of important. Chandan Jyoti is asking, what advancements are you anticipating in the field of astrobiology over the next 500 years? Now, I think 500 years is probably a long time. I've talked about this before, how our technology advances really rapidly. So how about over just the next 50 years? What kind of advances do you think we're going to see in astrobiology?
Wow. Oh,
That
it's
is a big picture pie in the sky question, I know. So
wow. So of course we will have more developed instruments. This is for sure. More precise, more accurate, more sensitive, and more compact. So like really small in size. This is for sure. For sure, we will discover more about other planets, and then understand more about Mars. This is for sure because many countries now and organizations they want us to go to Mars and to investigate what's there. Also, some missions are towards Jupiter's moons, the icy moons, where also we can also have some interesting things coming from there. But for the 500 years, ah, that's I don't know. I think that the key is to understand what happened on Earth first, um, uh, and the same. But the problem is because we have tectonics on Earth, we lost the first traces of life. Like let's say we have a gap of 1 billion years, and scientists they think that if we study Mars, we can have this answered. So basically, we need to use terrestrial analog to understand other planets, but in the same time, we need other planets to answer the question why we are missing the first part of life on Earth.
I think that's one of the first times I've heard it presented that way, and I really like that. That's a good way to look at it. That because of our tectonics, we lost information. Maybe using like Mars, we can get some of that information back. I like this idea.
Yeah.
Okay. Well, thank you so much. My personal last question, I always like to ask this. So you are still working on your PhD. So, I mean, this is kind of massive. You have a first author paper and you haven't even gotten your PhD yet. So congratulations on that. That is a big deal.
Thank you.
So what is next for you? What is next for the research that you're working on?
Yeah. So for me, first, I will in the short term, I will finish my PhD. next year, and I will probably apply for a postdoc later on, working on the same thing related to astrobiology. Um, um, for the research, for the instrument, and for sure the main goal is to be deployed in a mission to Mars and to other rocky planets. For sure, this is the ultimate goal of our team, and we're working towards that goal.
All right. Well, congratulations again on the paper. Congratulations on the discovery. Very excited for you and the future of astrobiology. For those of you who joined us late, Yousef is a doctoral student at the University of Bern and doing amazing things already. So thank you for joining us. I look forward to having you back when you have more discoveries and more information. So keep us in the loop. And thank you, everybody, for joining us today. Just as a reminder, the SETI Institute is a 501c3 nonprofit. We rely on your donations to keep programs like this running so that we can bring you more information, more interesting scientists, early career scientists getting the chance to talk about some great work that is coming out. And so if you are inclined and able, please go to SETI.org and click the Give Now or Donate button and help us out. And of course, do all of the things like share, subscribe, comment, and thank you again. We will be back next week. It'll be a morning show for those of you in the United States. It'll be, well, for us on the West Coast, it'll be a morning show. And we will have Frank and Lauren to give us another SETI Unistellar Citizen Science update. So join us next week, and thank you for joining us today. Thank you again, Yousef, for being here, and everybody have a wonderful rest of the week.
Thank you very much.